Hello, it's 2025 and fundamental physics has come to somewhat of a crossroads. We've got an abundance of evidence from astrophysics and cosmology which tells us that 85% of matter in the universe is dark. Yet despite pretty relentless efforts on both theoretical and experimental fronts, we are still no closer to actually uncovering what this elusive substance is. Now, the state of our ignorance is really captured by this plot, which shows that dark matter could really be anything from 10 to the minus 22 electron volt ultralight bosons all the way up to composite dark matter with masses above the Planck scale. Now, not only is this landscape of dark matter extremely diverse in the mass range that it covers, but the quite bewildering array of phenomenology that this then harbours. As such, in order to probe this as thoroughly as possible, we need different techniques which specifically target different regions. Now, up till now, experimental searches have largely focused on this range here, looking for so-called WIMP and WIMP-adjacent models with GeV scale masses and weak scale couplings to the standard model. Part of the reason for this is that at the time at which people started thinking about searching for dark matter, this was the mass range and the phenomenology which experimental technology available at the time was able to probe. However, in recent years, transformative advances in quantum sensing technology have opened up a host of really quite tantalising opportunities to search dark matter at this very, very weakly coupled regime. And that's something which I would like to explore with you guys today. So today we'll be focusing on just one part of this dark matter landscape, specifically so-called ultralight dark matter. This refers to dark matter particles with sub-electron volt masses. Now, in order for so light a species to be able to saturate the local dark matter abundance, they need to have extremely high phase space densities and as a result behave as coherently oscillating classical waves. This means they give rise to very different phenomenology compared to heavier particle-like dark matter candidates. As an example, if you have an ultralight dark matter field with scalar couplings to the standard model, and for the purpose of example, I'm just going to take those couplings to be linear, but note that similar phenomenology actually arises if the couplings are instead quadratic, then a direct implication of these couplings is that they cause the fundamental constants, for example, the fine structure constant, fermion masses, or the strong coupling constant, to appear to oscillate in time. And as a result, any energy and length scale that depends on these constants then also appears to oscillate in time at a frequency that depends on the mass of the dark matter field. So how then might we search for these time-varying fundamental constants? Well, one way is by comparing the frequency of two different atomic clock transitions, each of which depends on the fundamental constants in a very precise and ultimately different way. Now, the way in which the transition energy depends on a given fundamental constant, let's denote that x, is captured by a so-called enhancement factor k, which can be computed from atomic theory. As a result, it's straightforward to see that the change in the ratio of the two clock transition frequencies depends on the change in the fundamental constants, delta x over x, multiplied by the difference in the enhancement factors for your two different clocks. As a result, if you want to do such an experiment, you're going to really benefit from picking two clocks with as different k factors as possible, in order that for a given change in fundamental constants, you get as large a change in the ratio of frequencies as you can. And this has really motivated the development of more exotic types of clocks, such as highly charged ion clocks. Now, which fundamental constants a given transition is sensitive to depends on the type of transition that you are considering. Specifically, if you've got an optical transition, this is sensitive to variations in the fine structure constant alpha and the mass of the electron, and these typically have k factors of order 1. On the other hand, optical clocks are insensitive to dark matter that couples to quarks or gluons, and the typical k factors for this coupling is like 10 to the minus 5. If you do want to sense such couplings, what you need to do is instead compare an optical transition to a hyperfine or microwave transition, which identically have k of 1, such that your delta k for this comparison is also 1. Now, the whole kind of field of clock comparisons is set to be revolutionised in the very near future by the possible development of a nuclear clock. So it's been determined that thorium-229 actually has a low-lying excited isomer. And this is very, very exciting because the energy difference between the ground state and the excited isomer is 8.3 electron volts, which is actually in the optical range. And this is very, very, very exciting because it opens up the possibility of being able to drive this transition with a laser and therefore building a nuclear clock, so a clock based on a nuclear transition rather than the transition of electrons as we've been previously considering. Now, it turns out that in atomic form, the lifetime of the excited state of this nuclear transition is only 10 microseconds, and that's due to internal conversion. However, it's possible to extend the lifetime if you either consider thorium-229 in ionic form, so you therefore move the pesky electrons which are causing this internal conversion, or by doping this into a lattice. So if you do either of these techniques, it's possible to extend the lifetime up to sort of 10 to the 4 seconds. So this then becomes a stable transition. And again, this is something which is needed if you want to actually build a proper clock. So why on earth might we be interested in building a nuclear clock in the first place? Well, firstly, I mean, it's very, very exciting that you can actually potentially excite a nuclear transition. But actually, this has a number of really key advantages, some of which are going to be really key or specifically lend themselves to searching for new fundamental physics. So the first reason is that these nuclear clocks, because the nucleus is shielded by electrons, this means that the nuclear transition itself is particularly insensitive to external perturbations from, for example, electromagnetic fields, which is something that people that work with clocks are normally very, very concerned about. And the second, and possibly more exciting reason, is that the nuclear clock is actually extremely, extremely sensitive to the variation of fundamental constants. And the reason for this is actually due to a bit of a fine-tuning miracle, I'd say. So this is the one place where kind of fine-tuning is actually really helping us as fundamental physicists. So it turns out in the nuclear transition energy, you've actually got a cancellation between the electromagnetic energy and contributions from the strong force. And as a result of this cancellation, you've got kind of like MeV scale energies that have cancelled to produce an 8.3 electron EV energy gap. So anything that's then perturbing the transition energy, that's something that's going to be perturbing at sort of MeV scale, but the energy itself, or the raw energy, is like 8.3, so your delta X over X is going to be very, very, very low. So now, if you look, for example, at your how this affects the transition energy, you can see that what's effectively the K factor, which is this coefficient of the couplings, dark matter couplings, they're of order 10 to the 4. Okay, so this is for DE is for the coupling to the fine structure constant, so that's now 10 to the 4, whereas again for our atomic or optical clock it was order 1. And even more excitingly, you can see that for the coupling to quarks and gluons, it's actually 10 to the 5. Now, for the atomic optical clock, remember I said on my previous slide I said, it's only sensitive to alpha and Me. Well, in fact, it is kind of sensitive to the quarks and gluons, but this only enters by the reduced mass of the system, so Me over MP. So it turns out that atomic optical clocks have a K that's basically like 10 to the minus 5 for these things. So what we're seeing is that there's approximately a 4-order enhancement in the sensitivity of the nuclear clock to dark matter coupling to photons, and basically a 10 order of magnitude increase in sensitivity to new physics coupling to quarks and gluons. For me, this is like absolutely mind-blowing. I mean, if you said to me, I'm building a new experiment and it gives me a 1 order of magnitude increase in sensitivity, I'd be over the moon. But something that's potentially giving you a 10 order of magnitude increase in sensitivity is absolutely mind-blowing. So the way this changes things now is, again, you'd have to take a nuclear clock and you'd compare the frequency of that nuclear clock to a typical optical clock. But now our change or our difference in our enhancement factors are very, very large, and therefore we're going to have a very large or a much increased sensitivity to the variation of fundamental constants and in turn dark matter. So where are we with building a nuclear clock? Well, nuclear clocks have not been built yet. However, and this is again something which is like the rate of development of these things is absolutely astonishing. So in the last very much in the last few months, they've actually for the first time been able to excite this transition with a laser. So before they knew the transition was there, but they hadn't been able to radiatively excite it. They've now done that. And having done that, they've actually been able to then increase our knowledge or decrease the uncertainty on the transition energy even further by applying a frequency comb. And they're very much hoping that, within the next kind of 5 to 10 years, it might be possible to have a fully operational nuclear clock that it might be then possible to go and do these frequency comparison experiments with. So this really is a hugely, hugely exciting thing. I'm excited. Hope you guys are also excited. And it really could revolutionize, I think, fundamental physics searches in the near future. Okay, so we've talked about how clock comparisons can help us to search for time-varying fundamental constants, but there's actually another way that we can use clocks to search for time-varying fundamental constants, and that's via the field of atom interferometry. So an atom interferometer is just an experiment that measures the phase shift between spatially separated quantum superpositions of atomic wave packets. So it's basically analogous to the kind of interferometry experiments you probably did with light back in undergraduate days. But instead now we have the atomic wave packet itself that's being split, and what's splitting it is actually interactions with a laser. So we're using light, we're using a laser to kind of divide and recombine these atomic wave packets. So how exactly does atom interferometry work? Well, basically you start off with an ensemble of atoms in the ground state, and you apply a laser pulse to put them into a superposition of the ground and the excited state. And you let these things evolve for a time t, in which they accumulate phase, and they accumulate phase differently. And then you apply what's known as a mirror pulse to reverse their directions, let them evolve for a further time t, and then you apply a further beam splitter pulse, which interferes them. And you can see that the probability of being found in the ground in the excited state depends on this delta phi, which is the phase difference between the lower arm of the interferometer and the upper arm. Okay, so what you're essentially measuring at the end is this phase difference between the lower arm and the upper arm. So this space-time diagram is symmetric. So if there was no new physics, you'd expect there to be no net phase difference. However, if anything changes, for example, the energy levels or the external or the internal degrees of freedom, for example, as ultralight dark matter does change our internal degrees of freedom, that will end up with a net phase difference between these two arms, and that's something which you can record and measure. So in terms of actually doing this in practice, it's actually going to be done by what's known as an atom gradiometer, which is where you have two different atom interferometers separated by a long baseline. And there are many, many proposals for these long baseline atom gradiometers in the near future, including AION and MAGIS. And the second subtlety, compared to the diagram I just showed, is that instead of using a single pulse to separate and reverse the direction of your atoms, you're going to use multiple pulses. And each pulse causes momentum to be transferred. So this is known as large momentum transfer techniques, and it basically increases the space-time area covered by your atom interferometer. Now, the sensitivity to fundamental constants depends not only on the baseline, but the interrogation time and also the number of these laser pulses that you're applying to separate your lower and your upper arm. So if you want to have sensitivity to ultralight dark matter, not only do you need typically of order kilometer baselines, but you also need about 1,000 pulses. And in order to do this, you need your clock transition to be extremely narrow, i.e. you need your transition to be extremely long-lived. Now, the atom gradiometers that are proposed in the future work on strontium, which is a clock transition, which is an optical clock transition, and therefore this means they're going to give sensitivity to new physics coupling to the fine structure constant and also the mass of electrons. So let's just have a very brief look at the current state of play. So you can see that in terms of new physics coupling to photons or the fine structure constant, we've got atomic clock comparison experiments which are giving sensitivity around here. If in the future we were able to do a nuclear optical clock comparison, that would lead to a significantly enhanced sensitivity by about 4 to 5 orders of magnitude, as shown by this yellow line here. But it's not just clock comparison experiments that have sensitivities to this coupling, it's also atom interferometers, and this dashed line here shows what a terrestrially based atom interferometer may be able to do in the future. Now, in terms of the coupling to gluons, remember that atom interferometers are based on optical transitions alone and therefore aren't really sensitive to this coupling. Instead, the leading bounds come from clock comparison experiments, which again could be significantly enhanced in the future by the development of a nuclear clock. So we can see that the nuclear clock really is going to revolutionise clock comparison experiments. And the question is, could the nuclear clock also have a role to play in enhancing interferometry? I.e., could we build some kind of interferometer out of the nuclear clock in order to take advantage of its enhanced sensitivity to the variation of fundamental constants, particularly those dark matter coupling to gluons or quarks? So we had a long and hard think about this, and it turns out there are two ways, or at least immediately obvious ways, that you might conceive building a nuclear interferometer. And the first is similar to the atom gradiometer experiments that we've been considering earlier, which is to work with clouds of thorium-229 atoms. Now, unfortunately, thorium-229 atoms, as we mentioned earlier, only have a lifetime of 10 microseconds, which means that spontaneous decay becomes a problem. And not only does this mean that the maximum baseline over which you can operate is limited, but it also means that you want to try and do as few as possible laser pulses. So this means your LMT order, which typically increases your sensitivity, needs to be low. Of course, the advantage of working with thorium-229 atoms is that because they're atoms, they're neutral, which means you can have many, many, many of them in a cloud. And that means your shot noise, where shot noise is essentially 1 over the number of atoms in the cloud, can be low. So because of the issues with spontaneous decay, we thought, well, why not try and work with ions? Because, of course, when you build a nuclear clock, they're going to be using ionic thorium-229. So the advantage, of course, of working with ionic thorium-229 is that the transition now becomes very, very, very narrow. The lifetime is very long. And this means you can have long baselines and you can also do high LMT orders. The disadvantages are that the ion is now charged. So this means you can only have one ion in the cloud at a time. And that means your shot noise is going to be very, very high. So the question then becomes, can this inherently enhanced sensitivity of the thorium transition to the variation of fundamental constants overcome the difficulties with performing interferometry on the thorium-229 system in order to lead to new bounds on dark matter parameter space? And we find that actually it does. So on the left, I'm showing our forecasted sensitivity for the coupling to photons, which you can see is similar order of magnitude to typical atom gradiometer experiments. But for the single ion experiment, we can actually see that it does actually lead to an enhanced sensitivity to the coupling to photons compared to typical atom interferometers. The real power of this potential experiment, however, comes into looking at the coupling to gluons or quarks. So remember, we said that typical atom interferometers are based on strontium. Strontium is an optical transition, and therefore atom interferometers such as A-ion aren't really sensitive to new physics coupling to quarks or gluons. However, this is not the case for the nuclear interferometer. Remember, our K factor in this case was order 10 to the 5, and therefore the nuclear interferometer does turn out to be a good way of probing this coupling. And again, we can see that by doing interferometry with this system, rather than just doing clock comparisons, which I've shown in yellow, does actually bias some more parameter space, both at higher masses and also at increased sensitivities. So hopefully I've managed to convince you today that quantum sensors offer a number of really quite tantalising opportunities to probe fundamental physics, and I think it's something that we should really be trying to exploit. Hopefully you now have some idea of how atomic clock comparisons and atom interferometers can search for the variation of fundamental constants. And finally, I've introduced a bit of a wacky idea, the nuclear interferometer, which may open up a window to new parameter space in the near future, particularly looking at new physics coupling to quarks or gluons. So thank you very much for listening. I'm hugely excited about what quantum technology can do for us in the near future, and hopefully you guys are too, and I would love to chat with any of you at any point in the future. Thanks very much for listening.